We're going to show one way to solve the measurement problem of quantum mechanics. There will be part of the problem left, the part that is common with classical mechanics. There's a very simple way to state the solution. Because of the duality of states and measurements in quantum mechanics, collapse of a state is equivalent to no change of the state and a constraint on subsequent measurements. Let's go straight to details of collapse of a given state after a measurement that has a discrete spectral projection. The Luder's transformer projects the state to a sum of eigenstates of the measurement. Suppose for some experiment we actually measure something that collapses the state, followed by another arbitrary measurement. For the average of the product of the two measurements, we can use the cyclic property of the trace and the commutivity of the measurement with its own spectral projection to swap the action of the Luder's transformer from the state to the following measurement. The crucial property of the Luder's transformed measurement is that it always commutes with the measurement used to generate it. So the two measurements can be measured jointly in any state at all. Collapse of the state is equivalent to no collapse at all, but instead all the measurements must commute with each other. You may recognize this. A raw description of an experiment must be classical. That's an essential part of the Copenhagen interpretation. Not only the raw data is classical, the way we model how we collect the raw data is also classical. In this solution of the measurement problem, state collapse enforces this. Another way to think of state collapse is that you can't just measure anything after measuring a first thing. This is a mathematical statement of Bohr's often repeated insistence that measurements affect what other measurements are possible. There is a clear experimental necessity for this structure. For joint measurements we actually make, we can construct experimental joint probabilities, statistics. The probabilities we predict for them had better be real and positive, because the statistics certainly will be. That requires that measurements must commute, which state collapse ensures, thankfully. After so much insistence on commutivity, on classicality, is there anything that is not measured jointly? Is there anything that is not raw description? Algorithms of signal analysis, like Fourier analysis, are not. They generally transform the raw data in ways that do not commute with other ways. What is the residual measurement problem shared with statistical classical physics? When we throw a die, we know there is a 1/6 chance of a 6, but statistical physics doesn't try to tell us which throw of the die will be a 6. We hardly worry about this, but there it is. This will not be enough for some, but as far as I know, the simple equation on the third sheet is new and gives us this solution.